Welcome to Lesson 1 of our Electroplating Training Masterclass, the basic principles of plating. In this session, we're diving into the core fundamentals of electroplating: what powers it, what controls it, and what makes it work at the atomic level. Let's go step by step through the 13 key topics. Ready? Let's begin. 1. Electroplating and energy. Electroplating is essentially a form of energy conversion. We take electrical energy and use it to drive a chemical reaction, specifically, the deposition of metal ions onto a conductive surface. This process isn't natural, it only happens when we supply energy, typically in the form of direct current. Energy can't be created or destroyed, only transformed, and in every plating bath, we see this transformation in action. While several forms of energy are involved, thermal, mechanical, and chemical electrical energy remains the easiest to control and the most efficient to use. But before any plating can occur, we must overcome the activation energy required to initiate metal deposition. And here's the twist: we're forcing ions to go uphill energetically, turning dissolved metals back into solid form, something that requires precise energy input. That's the heart of every electroplating process. 2. Conversion of energy into chemical energy. Let's move to energy storage. When a metal dissolves in acid, it absorbs energy and forms metal salts. This is chemical energy being stored. Electroplating reverses that process. By applying electrical current, we convert that stored chemical energy back into metal. This makes electroplating a very clean and efficient way to recover or deposit metals. Compared to smelting or chemical reduction, electroplating offers better control over thickness, structure, and location. It's not just about making things shiny, it's about engineering surfaces with precision. And understanding how this energy transformation works lets us optimize efficiency, reduce waste, and improve repeatability in plating shops. 3. A definite amount of electricity. Now let's talk about Faraday's law. It's one of the most important concepts in plating. It tells us that a fixed amount of electricity deposits a fixed mass of metal. 1 ampere-hour equals 3,600 coulombs, and depending on your metal, that could give you a few grams of deposit. This means you can plan your plating process with mathematical accuracy. Whether you're coating 1 part or 1,000, you can calculate the exact metal usage. Just keep in mind, not all current is used perfectly, some is lost as heat or side reactions. So understanding Faraday's law also helps you account for efficiency and improve your process controls. 4. Connecting electrical resistance in series. Now we shift to circuit design. When you connect resistors or wires in series, total resistance goes up and current goes down. In plating, this can reduce deposition rates or cause poor adhesion. It's important to remember that every cable, connector, and busbar adds resistance. Too much resistance generates heat and wastes power, and may even affect bath stability. So clean, tight connections are essential in any plating line. If you ever have uneven plating, don't forget to check your circuit resistance as part of your troubleshooting. A little maintenance can go a long way here. 5. Connecting electromotive forces in parallel. In contrast, connecting power sources in parallel increases current while keeping voltage the same. This is ideal when you're running multiple tanks or plating large parts that need a lot of current. But this setup requires matching the voltages of each unit. If you mismatch, one rectifier can overload or damage another. Done right, parallel connections improve reliability and ensure that each plating station receives consistent power. It also gives you redundancy. If one unit fails, the others keep running. Just be sure to monitor current flow across all lines to avoid uneven deposition. 6. What happens in a plating bath? So what exactly is going on inside the bath? You have metal salts, usually dissolved with acid or complexing agents. These provide ions that travel through the solution. At the cathode, those ions reduce and deposit as solid metal. At the anode, metal may dissolve to replenish the solution or act as an inert conductor. Additives like brighteners, levelers, and suppressors control the deposit's texture, brightness, and internal stress. You must also carefully manage pH, temperature, and agitation. Get any of these wrong, and you'll see defects like burning, nodules, or poor adhesion. 7. Atoms, ions, and electricity. Now let's zoom in even further to the atomic level. Atoms become ions when they gain or lose electrons. In electroplating, we use positively charged ions, cations, which move toward the cathode to become solid metal. Electricity itself is just a flow of electrons, and these electrons do the work of reducing the metal ions. Your electrolyte must be able to conduct ions efficiently. Salt concentration, bath temperature, and ion mobility all influence how well your bath performs. And when problems arise, slow plating, poor adhesion, it usually traces back to poor ion movement or conductivity. 8. Covalent bonding, the sharing of electrons. Covalent bonds involve atoms sharing electrons to stay stable. In plating, we see covalent bonds in resist materials, organic additives, and plastic substrates. They don't ionize easily, making them useful for masking and selective plating. These bonds are strong and directional, which affects adhesion and chemical resistance. When plating on plastics or hybrid materials, understanding covalent bonding is critical to ensuring coatings don't peel or crack. Surface prep and chemical activation create the right conditions for covalent bonds to form between layers. 9. The polarization, van der Waals, bond. Van der Waals forces may be weak, but they're very important. These are temporary attractions caused by fluctuations in electron clouds, and they help control how additives interact with surfaces. In plating, levelers often use these weak bonds to selectively suppress deposition on high spots. They're also important in drying and sealing stages, influencing how films form and how smooth or water-repellent your surface becomes. They're not as strong as metallic or covalent bonds, but they're part of the invisible toolkit of surface engineering. 10. The metallic bond. Metallic bonding is what gives metals their strength, shine, and conductivity. In this type of bond, atoms share a sea of electrons. That's what makes electricity flow so easily in metals. When you plate, you're building this metallic structure one atom at a time. But for the bond to be strong, surface prep must be perfect. A clean, active surface ensures new atoms join the existing metal lattice, not just sit loosely on top. Additives help refine grain size and improve the strength of the metallic bond. 11. The ionic bond. Ionic bonds happen when electrons are fully transferred from one atom to another, forming positive and negative ions. In plating solutions, these ions float freely, enabling the bath to conduct electricity. A strong ionic solution means good conductivity and better plating results. But poor ionization or contamination will ruin that balance, slowing down plating or causing rough deposits. By adjusting pH, concentration, and temperature, you can optimize ionic bonding and ensure a stable bath. This is one of the secrets to consistent, high-quality plating. 12. Ionization of sulfuric acid. Sulfuric acid is a common additive in many plating baths. When mixed with water, it ionizes into hydrogen and bisulfate ions, dramatically improving conductivity. But it's also highly exothermic, it gives off heat, so always remember, add acid to water, never the other way around. This acid helps maintain low pH, which influences deposition speed and surface quality. It doesn't complex with metal ions, which keeps the bath simple and effective. That's why it's a backbone in copper and nickel baths. 13. Electrolytic conduction. And finally, electrolytic conduction, the heart of it all. This is the movement of ions in a liquid under the influence of an electric field. In plating, cations go to the cathode and become metal, anions go to the anode. Good conduction needs a clean bath, correct ion concentration, and proper agitation. Warmer temperatures help too, but too much heat can cause trouble. Keep your bath filtered and your chemistry in balance, and electrolytic conduction will do the rest. Smooth, even plating every time. Studio microphone conclusion. And that wraps up the 13 fundamental principles behind electroplating. Understanding these basics gives you the power to design, troubleshoot, and refine your processes with confidence. Stay tuned for the next lesson, and until then, happy plating!